This is exercise 13C and exercise 13G on graphs of exponential and logarithmic functions on page 440 or 457 of your textbook. So, graphs of exponential functions, we'll focus on that first. The graph of an exponential function means that it increases at an increasing rate. Sounds weird. But basically, if I have something in the form of 2 to the power of x, and this example of a graph right here is 2 to the power of x, as you can see, as I increase the value of x, let's say I'm starting from the center, let's say start from 1. If I sub in x equals to 1, I would get 2 to the power 1, which is 2. And as I keep increasing this power, it's going to increase exponentially. And so what happens is, as we go towards the right, it increases very quickly. But if I make x a negative number, is my overall value of f of x or of y going to be positive or negative? If I, for example, substitute x equals to -1, well, you would get 2 to the power of -1, which, according to our not log laws, sorry, in our index laws, is just 1 over 2. So as we decrease our value of x, it doesn't go into the negatives. In fact, it just stays right above y equals to 0, because there's no number you can write to the power of that gets you 0. If you were to sub in x equals to 0, you would get 2 to the power of 0, which is 1. There's no way to get 0, and therefore, this is what we call an asymptote. Have we talked about asymptotes in the past? No? So asymptote just means a line where the graph never touches. So if I was to draw it visually, it would be this. Not that. It would be this. Okay? If I was to continue this graph towards the left to a negative infinity, the value of y would get very, very, very small. It'd become 1 over 8, 1 over 16, 1 over a million. But it would never reach 0. Make sense? Awesome. That's what we call the asymptote. And moving forward, all our transformations with our exponentials and our logarithmic graphs refer to that asymptote. So in this case, what is the equation of an asymptote? Y equals 0. Because that's what my value can't be. Y cannot be 0. Awesome. So that's the value. That's how we draw the graph. Now I want to focus on the idea of transformations. So over here, we'll go look at the text in a second. But over here, we have this graph here. So the red one is y equals to 2 to the power of x, just in case you can't read up the back. And the blue one is y equals to 2 to the power of x plus 3. What's happened visually? It's gone up. Has the graph shifted left any? No. Well, it can look like it, but technically no. So if I was to continue drawing this graph, it'll keep going up like this and continue to be parallel. I know it can look like it's shifted to the left because the top of the graph looks a bit different, but it is purely shifted up. So just like with our quadratics or our polynomials, we've just added a plus 3 at the end, which means we increase our y value plus 3. In the case of our asymptote, what was it before? 0. Y equals to 0. What is it now? Y equals 3. So asymptote has shifted up 3 along with our graph. Make sense? Awesome. Let's go ahead and look at something like this. So in this situation, I've got y equals to 3 to the power of x as our red line. Our blue line is y equals to 2 times 3 to the power of x plus 1. We know that the plus 1 means a shift in what, Neve? What axis?
The y-axis.
Lovely, the y-axis. But the 2 times at the front, what does that mean? It's a type of, starts with D?
Dilation.
Dilation, thank you very much, type of dilation. Exactly the same as our quadratics and our other polynomials there. If I have a dilation of 2, it just means my value of y is multiplied by 2 before we add 1. 1, exactly right. Now, our asymptote is y equals 1 because our transformation is we've shifted it up 1. Make sense? Okay. Last transformation over here. So, once again, I've got the red line as y equals to 3x. And I've got my blue line as y equals to -3 to the power of 2x plus 4. We can see that plus 4 means my asymptote has shifted up. And I can also see that the negative at the very front of the equation means that the graph is the negative version of what it was. So it's reflected across the y-axis. So I can see over here that even though my asymptote is shifted up the same, it's got a negative function, which means it comes back down. Also, because it's to the power of 2x, now this is I'm kind of jumping ahead a little bit, but to the power of 2x means that it's kind of dilated or squished across the x-axis, so along the x-axis. Which, if you think about it the other way around, instead of thinking about it, how do I multiply to get that number? whatever value I put in, so let's say 3 to the power of x, right? If I wanted to get 3 to the power of 4, I would substitute x for 4. But if I wanted to get 3 to the power of 4 on this equation, let's ignore the plus 4 and the negative, I would have to have x equals to 2. So whatever value of x I put in has to be half of what it was before in order to get the same value. Does that kind of make sense? Yeah. In which case, our graph is just squished this way. And for those of you that are watching the recording, I mean this way. Lovely. So let's read this text over here before we move on. Here we go. Here we go. As the magnitude of the negative x values become larger and larger, the y values get closer and closer to 0 but never reach 0. So that's what we were talking about earlier. That is, the graph of y equals a to the power of x approaches the x-axis from above. Now, this is leading on to something we'll learn either towards the end of this semester or the start of next semester. Approaches the x-axis from above. The x-axis is said to be an asymptote, and we can write this as this one right here. As x approaches negative infinity, so if I'm looking at it as going this way, yeah, as x approaches negative infinity, y approaches 0. Does anyone want to guess what that plus at the top right means of the 0? It's not to the power of positive. It just means from the positive side. Yeah, is that what you said, Riley? Awesome. From the positive side, which means that I'm coming down towards the y equals 0. Not going up towards y equals 0. If I was going up towards y equals 0, it'd be like -5, -4, -3, -2, -1, then -0.5, you get the point. Yeah? Awesome. So that's just terminology that we will learn one day. In general, now, we've been looking at the graphs of if a is above 0, or greater than 1, my apologies, if a is greater than 1. Last lesson, for those of you that were here, we're looking at the idea of how do we solve that algebraically. But in general, we follow this rule. If a is greater than 1, we just graph it as we're used to, where we have this function right here that goes up as we go towards the right. If a is less than 0, if I keep increasing the power, it will decrease. So for example, if I have 0.5 squared, it's 0.25, because it's half of a half, isn't it? If I have 0.5 cubed, it gets smaller, and then smaller and smaller. So as I increase the value of x, increase the value of power, then my y value gets smaller. And so we follow this rule here. If you're presented with a negative value of a, that's when simplification comes in. So for example, let's say you get y equals to negative a to the power of x. Well, you know that one's just going to be the negative version of the graph. But if you get this, depending on what the value of x is, you can simplify. If it's an even number, you know that the negative, you can just remove it. If it's an odd number, you keep it. Pretty straightforward. Okay. Alright, so that is the graph of exponentials. Do I have any questions before I move on? I'm not going to graph this just because I can't be bothered doing a table. I think you guys know how to do table of values. No? Okay. So that's the exponential. Does anyone remember how do you describe logarithms? What are they? I'm looking at those of you from last lesson. What is a logarithm? It's the opposite of a Thank you very much. Opposite of an exponential. Hopefully you guys remember that from last lesson. So this is what we have here. Y equals to 2 to the power of x, being this graph on the left, and then y equals to log base 2 of x. So hopefully you remember that if I have, for example, a to the power of x, a to the power of b, that's a very weird b, there we go, equals to c, that can change in form to log base a of c equals to b. Those of you that weren't here last lesson, this might not make as much sense. Basically, all I'm saying is that in this form, I can convert the equations so that the variables stay in the right form. So base a of c equals to b. Over here, we're saying base 2 to the power of x, aren't we? So we have base 2 of x in log. Are we okay with that? That just takes practice to try and read for those of you that weren't here. Okay, as you can see, they're reflected across what line? Daniel?
Y equals x.
Thank you. They're reflected across the y equals x. Now, we touched on this a few lessons ago. Does anyone remember what the inverse is? I'm really worried, guys. I know it's a period 1 on a Thursday, but still. The inverse is what happens. Sorry, I couldn't hear you. Inverse is what happens when you switch the y and the x values. So the logarithmic graph is the inverse or the flipped version of exponential. However, our transformations kind of stay the same, except our asymptote is a little bit different now, isn't it? So let's go back up. Over here, I've got the basic graph of log base 2 to the power, not to the power, sorry, of x minus 3. Now remember when we did quadratics, I said if it's in the bracket, we do the opposite. Do you guys remember that? Yeah? So in this case, I've got minus 3 in my brackets, and so I move my asymptote 3 to the right. And so then I get x equals 3. Now, remember our asymptote for our exponentials was y equals to 0, or y equals to whatever value by our transformations. In our logarithms, it's the x value that's our asymptote. Okay? So we translated it 3 to the right, and we end up with this graph over here. Now, I'm not expecting you guys to be able to graph these pinpoint by value. Obviously, you guys can't calculate log. I can't calculate log in my head that quickly. But you are expected to be able to draw the general graph and then find the transformations from there. Over here, I have f of x equals to log base 2 of x plus 2. If I'm plussing 2 inside the bracket, I go left 2 units, don't I? My asymptote goes from x equals to 0 to y, so x equals to negative 2. Are we okay with that? Yeah. Here, before I continue, does anyone want to guess what this graph looks like? Log base 2 of 3x means that for whatever value of x I put in, I only have to put in a third of what it was before in order to get the same value, and therefore I get a graph that looks like this. Essentially, it's just, once again, squished this way. But this comes with practice. You don't have to memorize the transformations. That will come to you naturally. Okay, here we go. Okay. Graph of y equals to log base a of x when a is between 0 and 1. So when a is between 0 and 1, let's use the example of half. I have log base half of x equals to y. What you're going to be doing is you're going to be converting and find the inverse. Once again, what does finding inverse mean? We switch the x and y. Thank you very much. That is a process. We're going to do it together. So let's look at this over here. So f of x equals to log base 2 of x minus 2. If I'm trying to find the inverse, I don't know if you guys have seen this before, f of negative 1 of x. F negative 1 of x, sorry. Have you guys seen that before? That just means inverse. But let's focus on switching the x and y first. So would you agree if I said y equals to log base 2 of x minus 2? Same thing? Happy? Awesome. Let's switch the x and y. And I get x equals to log base 2 of y minus 2. Are we okay with that? Yeah. Now, using our form from before, I'm going to zoom back out so we can see it. This one right here, I know the base and the power. So I'm going to rewrite it. My base is 2 to the power of what, Riley? So that's the answer, y minus 2. My power would be x. It's really weird to wrap your head around. It'll come eventually. From there, I add 2 on both sides. I get y equals to 2 to the power of x plus 2. That's the inverse. And so, f of negative 1 of x equals to 2 to the power of x plus 2. If you draw or graph, both the original function and this function that we ended up with, they're reflected exactly across the y equals to x line. Because we're switching y and x, aren't we? Let's do one more example. Now we're going backwards from exponential to log. So, same thing. I go y equals to 5 times 2 to the power of x plus 3. Neve, what do I do to find the inverse? Switch the x and y, is that what you're going to say? Yep, switch the x and y. So I get x equals to 5 times 2 to the power of y plus 3. Okay. Now, I want the value with the power by itself, don't I? So I'm going to go ahead. I'm going to take away 3 from both sides. So x minus equals to 5 times 2 to the power of y. So from there, what am I thinking of doing? Divide each side by 5. You could write it as this, x minus 3 over 5, or you could write it as individual fractions. I'm going to leave it like this for now. 2 to the power of y. Okay. From there, I'm going to use my formula from before. Switch it around. So I'm going to say log base of what? What's my base? 2. Yeah, that's it. Of, now we don't write the power, we write the answer. So in this case it's x minus 3 over 5, which equals to my power, which is y, which I'm going to write on this side actually, just to make it a bit easier. So it all goes back to that original form over here, where we've got this function there in that form. I know it's a lot to take in. I'm giving you guys the double to work on these two exercises. Do I have any questions? No? Okay.